Maybe I will introduce Michael and John Hong can do the Q&A. So firstly, welcome to the seminar, everybody. Say good morning, good afternoon, good evening, wherever you are. I hope you're all keeping well. Delighted to have introduced today's speakers, Michael Lee from University of Alberta, well known to all of us. He's been an active member in the COVID Canadian National Task Force on COVID, mathematical modeling of COVID. And he's spoken in other seminars as well before. He's, as I said, professor of mathematics at the University of Alberta. He actually got his PhD from University of Alberta, I believe, and postdoced at Montreal and Georgia Tech, and collaborates with many people around the world, in Canada, in China, and other countries. And we're looking forward to his talk today on estimation of the proportion of population infected with COVID-19 using SIR models. Michael, please.
Okay. Thanks, Kumar and Jianhong for the kind invitation and also the introduction. Just before I start, I take this opportunity to, I do see there's some people from France joined. Just a while ago, I missed the talk that I promised to give in the Bordeaux seminar series. And this is the opportunity for me to say sorry. I really apologize. It was entirely my fault. Beer is totally innocent. Okay.
So
okay.
You mean you missed your talk?
It's my talk, yes. Not the, and okay, so I will talk about just what can we do for the to estimate the proportion of the population that's infected by the COVID. We're looking back in the spring. This is not about a forward projection. Okay, what proportion will be? This is actually what has been infected by the COVID during the first wave in the spring of 2020. And much of these kind of research has been published using seroprevalence tests results, and which is called antibody tests, all around the world. And I haven't seen much results of estimation of such a proportion using our kind of mathematical models. Now, the question is, can we do it? And then how we do it. Okay, so there are two parts of the talk. The first part is I will look back in the early spring or during the first wave, the kind of modelings we have been doing, many of the modelers have been doing, and what we have been doing with Alberta Health. We're the main modeling support, our group for the Alberta Health during the COVID. And then the second part is, now we have all of the data we need from the spring, and then can we actually do a good job accurately estimate the kind of information we need. One of them is this proportion of the infected population. And now, if you recall, early in March, when the cases hit Canada, North America, and some coming from China, some coming from Europe, then a lot of model projections during those time, almost all of them projected if we don't do any kind of control measure, and then there will be 60% or up to 70% of the population will be eventually infected. That was quite astonishing. And I think the government did respond to it. Most of the provincial government did respond to it. For example, Alberta Health, we projected about 60% of the Alberta population would be infected. So we had the first case identified in Alberta on March the 8th, and the province is completely shutting down on around March 20th. So in 2 weeks' time, they shut it down. The university campus is entirely closed. Everything moved online. and all the gatherings banned. If you walk outside, you need to keep this 2-meter distance from other people. So it was a very, very strict. And this, so as a result, we had a very mild first wave. Okay, the highest daily case, new case in Alberta is about 350-ish. Okay, so and now we can reach 2,000 per day cases a while ago. So that was a huge difference. And then, but if you look back, around the time in, I think in April or May, people start to do antibody tests in the population, sampling in the population. And the results is quite also astonishing. For example, in Sweden, we know that there are some form of social distancing, but much more relaxed compared to what we had here in North America, well, in Canada at least. And so the antibody test, I remember around May from Stockholm, shows that the people with positive antibody results is probably at most 15% of the population being sampled. And that's far from 60% or 50% models have predicted. So that's sort of a, if we look at this as modelers seriously, we were entirely wrong, okay? In the early spring, we don't have to hide it. We don't have to shy away from the mistakes. I think we're entirely wrong what we did in the early. But then the excuse was, we have a good excuse because we don't know much about this new disease. There's very little data at the beginning. And so that's actually reasonable. There's a good excuse for us to make mistakes. So that's why I in the second part, then the question would be, now we have all the data we need, okay, we can get our hands on. Can we do retrospectively, can we do a good job? Do some estimation so that it can be validated from the, say, seroprevalence, the antibody test results, which are, a lot of them are known now. Okay, so that's sort of the purpose. But before you can actually make sure we do accurate estimation with more complete data, we still have to understand what was the reason we are all wrong. It's not the one person, the two groups. I think all of us got it wrong. So why is that? And so that's the first part. Okay. The first thing I want to talk about is the data, because this is really, when we do the abstract modeling, sort of the things I used to do when I was young, we never seen any data. We don't care about data. It's all about a model. You look at the behaviors model, solutions of differential equations, you prove things rigorously. But the problem occurs when we kind of associate the data output or fit the data output to data. That's where the problem occurs, okay? So first of all, let's understand what's case data. Either you look at these are reported cases or confirmed positive tests. You either look at a cumulative over a period of time or daily new reported positive cases. These are what we mean by case data. And what are these? And how is that different from our model predicts? The question I ask is, do our models, transmission models, predict cases? Okay. If I think most of us probably working on some form of transmission model, some are simple as what I use as IR, some as EIR, or more elaborated models. You probably, it's a good practice to look into your model and see which part of your model, what quantity out of, what kind of output out of your model is case data. Okay, you probably find out there's nothing in our model that should be the case data. Okay, the transmission model. So there are many models that predict cases. I think I remember in early days, in the last year until the fall, the most accurate predictions of the cases comes from a group from University of Washington, but not their modeling group. This is their IP kind of group. They're using these sort of more statistical model, probability type of models to predict using the past cases, predict the future cases. They've done a great job and everybody referring to their projections. But those are not done using our transmission models, right? The transmission models are great, but it has limitations. We need to understand our limitations so that we can then we can find a way to do better. So what are the limitations? So first of all, let's understand the case. I'm sure you have seen these pictures many different occasions, at least a few times in my talk. I'm showing a picture of an iceberg, and there's a part that showed up on above the surface, and that I call that represents the part of the iceberg you can observe. Okay, that's the case data. You do some tests, you identify that some infected people that are some of the people that are infected. Those are the cases. But then there are a whole lot of the infected people at the same time that the surveillance system didn't pick up. They didn't go for a test, or you missed them in the contact tracing. And that's the part hidden below water. So the entire iceberg are the number of the people who are infected at a particular time t. This is a snapshot of I of t, okay, of the entire infected population at the time t. And some of them being identified, but there's a whole lot, or it could be a few, we don't know, that are hidden. So people in epidemiology or in surveillance, they understand this. They know that for each case you identify, there are a few cases that you miss. You couldn't find them, and just a matter of how many. And so here, roughly for SARS, for the first SARS epidemic in 2003, from modelings or from other analysis, you can kind of figure it out. The case infection ratio, which is the ratio of the tip of iceberg over the bottom, the missing part, okay? That ratio, we call it the case infection ratio, is about 1 to 5. For each case, you probably identify you miss 5. So that's very small. The reason being that SARS, there's very little asymptomatic infection in SARS, first SARS. Seasonal influenza, if you look at the US CDC, they've now published their model estimations on their website for seasonal influenza. You figure that ratio is at least 100, 1 to 100. That's huge. Right? So there are a lot of people infected are not being tested. And so what is the case infection ratio for COVID? So that's really one of the things we would like to estimate from the model. And right, so what do our model predict? Our model predicts the entire iceberg. That's all the people who are infected. Our model predicts infections. We don't predict cases, infections. And we're trying to use the data on the tip of the iceberg and try to predict the entire iceberg. That's what we were trying to do, basically. And obviously, if you know the ratio, then that's easy. But the ratio is part of the estimation. Right? So it's unknown, that number. Okay, so I hope I kind of explained this. And, so let's just take a standard SIR model, but I would kind of reinterpret the quantities in here. The S is still the susceptibles. The I's, I call them infected. Infected means include people who are infected but not yet infectious, and also included people who are infectious, okay? And I skipped the exposed class, the E. I intentionally not including the exposed class E here. It's not like I don't like SEIR, it's that SEIR performs worse than SIR for COVID, and I'll show you later. And so the I here included all the infected, including infectious and non-infectious. And the transmission beta here is going to be averaged over all of the people who are infected. So for people who are not infectious, you can assume their individual infectivity is 0. And then there are some people who are highly infectious, super spreaders. So this beta is averaged over all of these infected people, okay? And R here, I don't call it recovered. I call it, these are, R is simply a holder of all the confirmed cases. So rho of I here is the term that's being testing, you do diagnosis, you identify these positive cases, and then you move them into the R. And then the R, of course, they could die and they could recover later, right? So R, again, doesn't come into the system much. It's just simply a holder of the recovered cases, okay? So there are two other terms. The rho of I here is, this is the part, newly confirmed cases. This is the part in my model that's going to be fitted to the daily new cases, okay? The time units, we set it as day. And then this is just, there are some people who are infected but never been tested, and they might recover on their own, okay? Those are people just asymptomatic, and we just never know them. And they probably don't know they're infected either, okay? So that's the, I cut the transmission model almost to the bone. If you remove any of these, you probably, this is not a reasonable model for disease transmission anymore. So the reason for that is I keep the number of parameters that need to be estimated from the data to the minimum, so that I reduce what a statistician called overfitting. Overfitting just means you got too many parameters for your data. And so for them, it's kind of, if you look at it, using a linear model for regression, the count of how many, if you have too many, is quite simple. It's solving a linear system. But so it's easier for them to cut down their number of parameters so that they don't have overfitting. But for us, we don't have much choice. I cut it down to the bone. I still have overfitting, or what we call nonidentifiability. And that really is the root cause of all the mistakes we made, at least my mistakes, a mistake I made in the early spring. So that's the model. And here, for easier just presentation, I fixed this kind of recovery rates. I fix it around 10 days. When we actually do it, we actually allow it to a wider interval, use a uniform prior and then fit it. But here I just fix it for simplicity. So there are only actually 2 parameters I need to fit here, 3 actually. The parameter wise is I got a beta transmission coefficients, and rho, I call it the case infection ratio, which is unknown to us and need to be estimated. And there are another parameter that we don't know, that's the initial condition of I. At the time we start to do the modeling, say even when the first case is identified on March 8th, we still don't know how many people are out there which have been detected. So that R0 is also a parameter that needed to be estimated. So there's 3 parameters, but we only get a case data. Okay, so that's where the problem is. Okay, so here's a kind of an intuitive way to see why we have non-identifiability. I cannot uniquely fit, given the case data, I cannot uniquely fit the value of a beta and rho. Even if I fix the I0, it's just between beta and rho, I couldn't independently, uniquely fit these 2 parameters. The reason is this, okay? If I gave a value, any value to rho, let's say this is like a SARS. I say rho is beta with like a 1/5, or yeah, 1/5. And then I only have 1 parameter to fit. Okay, I can fix I0, for example. And then I can easily fit beta. from the case data. There's no problem with that. Okay? So, but for different rows I pick, if I pick a row as 1 over 100 for like influenza, and then beta will be different. I can also uniquely fit beta, beta will be different. If I pick a row anywhere between 1/5 and 100, I have a different value of beta. So you can see that the best fit value of a row and beta to the case data, they have a functional dependence. When you change your row, the beta changes with it. Okay, so that's non-identifiability. You cannot uniquely fit them independently. Okay, so and here in one of our earlier papers in the Journal of Infectious the Disease Modeling, Jian Hong's paper, the Jian Hong's journal, we kind of showed people how you visualize this functional dependence. So the same model there, and we only fitted the beta in row. And the surface, what you see here, the surface, this is the likelihood function for the parameters. And the best fit, the highest, the maximum likelihood is on the top in yellow color. You kind of can see here, there's a line on the top that's flat, okay? So this is the maximum likelihood. There actually, there's a line that's actually have the same maximum likelihood. And if you look at the corresponding parameters on the plane, which gave you the maximum likelihood, you project this down onto the beta row plane, you get this almost like a line, straight line. Every point on this line, you get a pair of a beta and row that give you the same maximum likelihood. And then, but the worst thing is, you pick two different values, two different pairs, and then you simulate, and you do the projection, you get different projections. Both of these pairs, all the pairs on this line give you the same fitting, the best fitting, but they produce different projections. So that's non-identifiability. Okay. So you can't trust the fitting. The fitting is not a test or not a validation of your results, okay? Because you have an infinite many pairs of beta and row values, which are best fit values, but they give you different projections. So that's why we all get these high, really extremely high, even though we have good fitting. So this is the fitting to the data in the early part, and this is the projection. Okay? So they all have a good fit, but the projections are really different. Okay? And then you can also visualize this from the posterior. So we're using Bayesian inference, MCMC. So you kind of give a prior distribution for your parameters you want to fit. We usually give a really wide uniform prior, and then the MCMC produces a posterior distribution for your parameters. If the posterior looks really like a probability distribution, you have a mode, and then that gives you the best fit value, and you can get a 95% confidence interval from that posterior distribution. Here, this is the posterior distribution for row. This is the posterior distribution for beta. You can see the top is almost flat. Here, beta is very sensitive, okay? So it doesn't have a very wide interval. You cannot like vary that much, but within the small interval, there's no apparent best fit value at all. So they all have the same probability to be a best fit. So that tell you, for people who have run these sort of things, you're in trouble when you see this kind of posterior. So this is one way, also a way to check to see your fitting is whether it's problematic. So these are the two evidence of the non-identifiability. We have so even though you can show people that your model output fit the data perfectly, but that's not an insurance that your projection in the future is reliable. That's the implication of a non-identifiability. The reason this occurs in epidemic models is not that epidemic models are wrong. It's just that we don't predict cases. When you fit the infections, the cases, there's a percentage, that rho, that case infection ratio, which we don't know, okay? You cannot back calculate the infection from the case data. There's unknown fraction there that need to be estimated. So that's the challenge. That's why we always run into this. I cut this almost like a minimal model for COVID. You know, you cannot cut this anymore. We still cannot ignore, cannot get away from this non-identifiability. You can imagine if you add exposed class, the problem will be more serious, right? I want to say just a few words about why we always use SIR and not using SEIR. It's not like I hate SEIR. I mean, one of my first theorems in the epidemic model was on SEIR. So, but a lot of times the mathematicians has the leisure to, stay away from the real epidemics. So we look at it from afar. We think abstractly. We look at some abstract model, even look at, do some abstract analysis, and then look at the insights we get from these abstract thinking. But that's not what we have been doing with Alberta Health. We could totally do that, of course, but because as we were called upon by the Alberta Health to provide modeling support, my attitude is we are Albertans. This is something that we do well, and we should provide support to support the government, right? And also we know that people die from this disease. A lot of people die from this disease. If we can provide anything that's useful for the government to decide on good policies, and yeah, we should do our best to do that. And so the kind of the work we had with Alberta Health is that the kind of a research problem comes down from the Alberta Health, from the chief medical officer of health of Alberta Health, and all the way to us, and translated through the way by some Alberta Health people who knows about modeling. And we run it with a model, and we then send our results back through a few layers of translation into language they can understand, all the way back to the committee run by the chief medical officer of health. And then the results will be used as evidence to support their, as part of their evidence. They have all kinds of evidence, and to support their public health recommendations to the premier and cabinet. So I've been doing this for 20 some years, and finally I have a chance that our results actually reach the policy level. And I told myself I'm not going to mess it up. I have to be very careful. So that's where I don't want to use anything that's complex. I want to use the simplest possible models, fewest possible parameters, so that I'm sure about the values and the parameter values estimated. So here's something about the model selection. That's just picking simple models or more complex models. So there's a pros and cons. Complex models, of course, are more realistic, but then also complex models has more parameters that should be estimated from data. And then that could lead to a higher degree of sort of uncertainty in your estimation. So there's a standard way to something, a procedure using information criteria. One of this is archaic information criteria. It's called AIC. And some others called Bayesian. If you're using Bayesian or Bayesian information criteria, the BIC. The AIC roughly says defined by two terms. One term is this is the related to the error between the fitting. of your model output and the data. Okay, the smaller the error, the smaller is this term. And this term is the penalty term, that K is the number of parameters that you have to be estimated in your model. N is the time points in your data. In our data, we have, now we have about 80 days after the whole first wave, but at the beginning we have about 15, 20 data points only. So this is a much smaller number than we have for SIR. We have 4 unknown parameters. And so this is bigger. We're in this case. So the K showed up here and here, but this is an increasing function of K. When K is bigger, you got more parameters, you got a higher penalty. So the smaller the AIC, the better the model represents the data. So there's a kind of, you can use this to determine based on the data quantity you have and the error fitting, and then you increase the realistic, how realistic complexity of your model. So the K increases. So that kind of give you a balance, determining what is the most suitable model for the problem. So I think I gave this talk early at a Fuse before the COVID. Oh, here's Canada, right? So we did a simple comparison between SIR, SEIR. In the SIR model, if you add an E compartment there, you introduced 2 parameters, unknown parameters, epsilon that has to do with the latent period, and E0 is the initial condition of E, which is unknown. Do we gain any data when we introduce a new compartment? No, we still have the same data, the cases. Now, instead of fitting 4, I'm fitting 6. And then you have to think about it. Yeah, SEIR is more realistic than SIR, but I have 2 more parameters to fit with the same data as before. Do I gain that advantage, or do I lose that advantage by introducing SEIR, introducing an E? Yeah. So we did a sort of a fitting, and we look at the AIC for SIR, it's 174, the other one 185, and the difference is 12. Anything bigger than 10 is basically, that means this should be discarded, basically. So SEIR is definitely worse in performance in that. So that's why I'm saying I want to be sure. So we always use SIR. That's just our call. Okay. So SIR, in our point of view, performs better than SEIR when you look at the data. And okay, now we have had a lot of trouble projecting and forward during March, early March. Okay, we try to give the province a more realistic kind of a projection ahead of the time, but we have a lot of trouble. And then we thought, okay, maybe we only have a part of the, we haven't seen the peak, right? We have a part of, just early part of the data. And maybe if we have the entire epidemic curve of the first wave, we can do a better job. Probably the nonidentifiability was probably gone. So around April, then we realized Australia, the first wave is finished. So this is Australia COVID-19 case data around April 19th. This is the end day. So they have an entire epidemic curve. So why not we fit our SIR model to the Australia data and see what happens. So we tried. We're using the new cases. You could also use the cumulative cases. That's the solid line. They're sort of equivalent kind of data. They're not independent data. They're just equivalent data. You can use one or the other. So this is the fitting. The circles are the cases, the new case data. And the solid blue line is the mean of the our prediction interval. And between the dotted lines are the prediction interval. Okay, so there's kind of still pretty wide interval. That's probably not avoidable because it is a simple model. But our mean tracks this case data quite well. I mean, this is very well. I mean, the difference is very small here. So I thought, well, this is great. And then let's check the posteriors. This is the posterior for rho. This is so concentrated. For beta, it's also concentrated. So that doesn't show any non-identifiability whatsoever. So we said, well, this is great. So we should be very happy. And but then we thought, well, maybe we check one more thing. We check how many people are infected. We want to check the IT. So this is the corresponding projected ST, which is blue, and IT, which is red. Okay. You see, this is the total population, basically, at the beginning. It's about 25 million, right? And for Australia at the beginning. And this is at the end of the first wave. It becomes like a, yeah, well, it's become 0.5. It started from the 2.5 and it dropped to 0.5. It's a huge drop in the, so there's a lot of infected people, right? Anything you lose here in our model, we didn't even count the natural deaths, okay? You probably, the only death is due to COVID. So the loss in, this is also like a final size, right? There's the loss of your susceptibles are entirely to the infection of COVID. So you can easily compute the infected proportion here, okay? So S0 is 2.5, whatever the percentage, whatever the units, and ST, capital T, is somewhere around 80 days, this is the end, or 100 days. So you can see that's 0.5. And then divided by the proportion, the entire population, you got 4 over 5. So you got a 4/5, which is 80% of the population are being infected during the first wave in Australia. Well, I mean, if you look at that, this is perfect, right? The perfect story that you only suffered about 300 cases per day at most within about 2 months' time. And then you achieve the herd immunity without vaccination. That's a beautiful story, but who's going to believe it, right? So that's still something's wrong here. Even though from the fitting, everything looks fine, but the prediction on the infected proportion is way out of the several magnitude wrong, right? So in Australia, it's probably 1% or 2% of the population being infected, okay? We're projecting this 80% with a perfect fitting, right? So that's sort of a worrisome. So we try to test it a bit more. We say, what if we use only half of the data from Australia, just half before the peak time, okay? Use this part, see what we have. We fitted it here. So the fitting is very good. The projection is horrible. The cases projection, word projection is huge number. So this is the fitting at the beginning, but this is again the repeat of what we had with Alberta case. Okay, if you only use, so we see that non-identifiability happened again here. So there's something definitely wrong. So we're trying to understand what was wrong. Why are we seeing this? Okay, so the conclusion is, now that case infection ratio shouldn't be a constant. It has to be time dependent. Constant just won't work. Okay, they give you strange things. So then you need the data to inform the kind of time dependence of this case infection ratio during the epidemic. So where do we get these data? So that brings us to, I was supposed to finish at 4. It's almost done. I'm just talking about the results now. When you understand the problem, you can easily find the solutions, okay? The hard part is we don't know where's wrong. So these are the hospital and physician visits during the seasonal influenza in the US. CDC published these, you can search for them. And the different colors for different ages. You can see that at the beginning, there's very few people going to hospital, seeing doctors for their flu symptoms. And then it goes up and then plateau and then declines, okay? The shape is so kind of uniform across the ages, even though the magnitude is different, okay? And your peak time of the cases is somewhere between these plateau period. So the plateau period will tell you where the period where the peak occurs. So we take this, we call the CT here, we call it the cases, okay, which are the data. And then the HT, we call this health-seeking behavior. It's defined by these curves. We kind of average it out. This is for influenza, of course, and average it out to get a curve, single curve. We call it HT. So we take the ratio. This would be the case over hospital visits, because hospital visits, usually they would do a test for you. This is the basically almost like the positivity of the tests, right? And this is kind of how many, the probability of a test that shows positive. And then we multiply a scaling factor, F. This sort of indicate for an infected person how likely this person is going to seek help to see a doctor or get a test. So this is an unknown factor. We just assume it's a constant. But rho of t can be informed by data. But of course now we have all this data for COVID from Alberta Health because all the tests is being triaged through either phone calls to Healthline or online assessment forms. So they have the records of that. So we get these curves for COVID for the spring, only after spring, not during spring, right? Only after spring we got all the data. So now our question is, with all of these, can we do an accurate, more accurate estimation? Okay. So we put now in our SIR model where we usually have a rho, we replace it by F times rho 1 times T. Rho 1 T is calculated or sort of fitted to the data of the case over these curves, hospital visits and tests. So that's basically known there. But the F is unknown, that need to be fitted.
Sorry, Professor Michael. So
yeah.
You're saying hospital visit of those cases or hospital
just
cases?
Anybody who called, who had been triaged, referred for a test.
Okay.
Right. So when you call, they will talk to you and ask you about symptoms and decide whether you need a test or not a test. And then of all the people who were referred to the test, they will get tested. So these are how we kind of, as a measure of a health-seeking behavior. Yeah. So, and if you don't call, they won't test you, right? So that's sort of like a replaced hospital visits because nobody's seeing a doctor during the spring. Doctors' offices all shut down. So that's how we, but we do have these data. Now you can see the projection. Now this is about the end date is starting date is early March. This is about the end of May, early June before we opened up. Because after in June, the province opened up. This is basically during the social distancing. The case data, so this is very tight fit, right? And that's that. And then this is the rho we fitted to that rho of t curve. Okay. We didn't use the data, we just fitted the data. This is the shape. So the peak is around this time. This is the I. The highest I number in the mean, there's a huge interval here, of course. This is about 10,000 per day. There are 10,000 people who are infected when the case is only 300, 400. Okay. So that's sort of the ratio you can see already there. And this is the S. So you see not much of a drop here, but it could mean, there's a lot of unknowns still, but this is the average there. This is 95% interval. Okay, so this is the mean here. Now you can compute now the proportion, beginning total population, at the end of the time, the population, the ST, you can read out from that blue curve and divide it by the regional population. We got about 2% of the population being infected in Alberta at the end of the first wave in June, in the end of May, at the end of May. And then the case infection ratio, you can read it out from this F times 0.1 of T. It's sort of between 0 and 0. At the beginning, it's kind of low. At the peak time, it's high, okay? And 0.06. And if you converted it into the case infection ratio, it's about for one case identified, you will have probably 17 cases you don't know. So the intuition from Alberta Health surveillance people, they think it's about 1 to 10. So we're in the right ballpark in there. Okay. Or the intuition agrees with what we did here. And you could also do some cumulative cases over, which is the integral of all the incidents, and then times this case infection ratio here, right? And then over the entire population, the entire population entirely infected. The loss in the susceptible. It's similar. It's about 0.06. So it's 1 to 117. It's sort of higher than the COVID and then the SARS, but not as big as the influenza. And so, of course, then we wanted to validate these things. Alberta Health did 2 antibody tests during the spring, and their number is in our prediction interval. It's comparable. So they were happy to see our model results. So they trust our model a bit more after that. And we did this sort of in June and 2020. Right. Yeah, whatever I'm gonna say. Okay, so I think this is the end of my talk. I just wanted to make a comment that the good fitting shouldn't be used as a validation. Okay, it's not a validation. Good fitting with the case data, with your data, and you can look at the IFT to see if it's way out of line, or you can compare it with compare IT with the seroprevalence results. That might be independent data to validate our modeling results. So that would be the end of it. And thank you very much.
I can see Kumar is nodding, so he must be impressed. I'll let Kumar to raise the question first. Anyone can raise the question directly, or you can send a chat.
Well, firstly, let's thank Michael for a really excellent talk. I think it's a very, as usual with your talks, Michael, I find it very clear and they shed a lot of light on the question. So in your calculation, you did this row 1, you used hospitalization or going to a hospital as a kind of proxy. Right. And then you scaled it by that. Scaling is okay. It's the scale, that point is that F is okay.
Yeah. Well, this is not quite new to us. Actually, we have been doing influenza predictions for Alberta Health for 5 years, and this is exactly the kind of data we use for influenza. We still don't have these data row T for the current season because it's early in the season, but we have 10 years past season data.
Yes,
we can use to inform that. But for COVID, we don't have that in the early spring. Right? So that's the difference. It's the data that's people seeking tests. It's not really hospitalization. How many people are asking for get a test? And that's the curve.
And would that not be skewed by our initial ability or lack of ability to provide tests?
Certainly. That's certainly true. We look at a few things: the number of tests that they performed, and also there are 2 forms of there's a health line calls. There are also the website referrals. We look at all of them, If some curve really different from the others, we try to balance it out. We don't want it to be influenced by one type of the curve too much. Yeah.
Okay. Very interesting.
So I heard from multiple sources about your work on influenza prediction in for Alberta for not quite a number of years. So I have the same questions as Guehong Fan, and any of this work published at all? I know you don't.
No, we never
publish
these things.
Right,
I'm just very bad at this.
Yeah.
We wrote a draft. We should get it published. I'm finishing a manuscript on this one. We'll try to publish it.
No, it's a success story. I heard from many other sources, not from Marble Inside community, but from other sources. But we would like to really have the story documented.
Sure.
So another question. I know this is highly relevant, but I don't know how to do it. I should was planning to have a group of people working on it. It's now we have this number of tests, available test positive ratio. It's relevant to what you say, but it's not the same. So can you just do using the test positive ratio as the index to?
Yeah, possibly. If they don't change their policy in the test too much, I think that's still fine. Yeah, if during that period they kind of switch back and forth too much, there is a little bit of switching, right? They sometimes test but as long as it's not too much, it's totally possible.
Great, thank you.
Yep.
Other questions? This is Yadgaria. Yureji, you want to talk, or do you want to ask a question? You wanted me to read the questions. Yadgari. Maybe I should read the questions. Thank you for this interesting question. Did you compare SIR and SEIR for different scenarios? For example, different population size.
No, we just used the Alberta data. No, we actually back then were using Wuhan data. We just used that, and it's not really. We don't want it to publish the size that SIR is bad, SIR is good. It's easily get out of the context. Then it's not what we're trying to say. We're just trying to say is that you have to make sure for yourself that the model you're using is the ones you trust the most, right? It's not like everybody using SEIR, I should use SEIR. You should know why. So that's just a demonstration that a little bit more complex model may not be the best model you can use.
That's the same rate. That's the same reason you did not include the asymptomatic infections, Michael?
Asymptomatic infections, well, first of all, you don't have data on that. Right?
All right.
You don't have reliable data on that. So if I introduce, so basically I told my students, if you want to introduce a compartment into your model, you first ask, do I have data on that? If you don't, you're in trouble because there gotta be a couple of unknown parameters associated with it. And also not counting their cross infections of these betas, those are deadly, right? You still have the same set of data. You're introducing new compartment with no data on it. You got to lose. You're introducing uncertainty in your estimation. So you got a much larger confidence intervals actually.
Thank you. Any other questions?
There is something from Egypt Yardi.
No, that's the one I read.
No, there's a long one.
Yeah. Egypt, please.
About the effect of the contact heterogeneities in the infection, that also has something to do with Jiang Hong asked about the asymptomatic infections, right? And no, as I said, I'm not thinking about this abstractly. That's not my objective doing this model. I wanted to give some estimations, some projections to the Alberta Health, to the health authorities who make recommendations to the government. to decide on there. This is not something that you can use somebody else's parameters to do projections. That's not reliable. I can't give that kind of a projection to the Minister of Health. Okay? That's misleading those policymakers. I would have to do something that I can defend. When they ask, if they ask me, where did you get your parameters from? I have to be able to defend it. So when I introduce all these heterogeneities in the model, I mean, where do we get reliable parameter values? If you cannot defend it, do I expect them to trust me more because the model looks fancy, right? So this is a different kind of modeling. I'm not saying, you know, we shouldn't look at these things abstractly, thinking in abstract terms. We're really good at these, but those don't necessarily give you reliable projections. We have to know that, okay? They give you interesting projections, but not reliable, not necessarily reliable. And here, reliability is I mean, if I misled the government, they could blame everything on the modelers. Well, they didn't, but so that's why I didn't really show you all the results at the end. I don't want these things get out before they publish. They let people know, right? So, but I can tell you that the estimations are validated by the antibody test data.
Thank you for your answer. I mean, in the FIR model, there's this beta coefficient is just a number that governs the spread.
Oh, no.
But
beta
realistically, it is more than just one number. So that's what I meant.
I apologize. I didn't show you the beta. Beta actually depends on T. Beta has a declining curve. That's also fitted. We allow the beta because of the social distancing. That curve somehow didn't get included.
Does it also depend on the location?
No. It's an average over the entire provincial population. And but it does have a time dependence. It has a declining trend. The slope, the down slope is fitted. Okay. So that's otherwise this wouldn't be right. I apologize. I forgot about that part. Yeah, it's not a constant beta we're fitting. It's a time dependent data to incorporate the effects of social distance. We didn't add any, we do have another model, which we did a better estimation, this age structured model. We have 3 age groups, young and adults and older. So we have a much finer results now. We can tell you the proportion of infected in each age group, young and old and other things. But that's a much longer talk, so I don't want to.
Now I have a final question from somebody knows about Alberta. So it's from Cornell. He asking you, do you have to run the model for Calgary and Edmonton?
Yeah, we did, certainly. They always ask us to do the zones. We have about 5 geographic zones. We always run them parallelly. We don't look at the connection among these zones. Okay, we run them separately. Yeah, the results are really comparable. Yeah. Good. Since transmission between them is unlike, yeah. So we don't count the travels between these. This is pretty much shut down. Everything's shut down. Yeah. Okay. So
thank you. So Michael, I just want to thank you. And Kumar and I was joking before. I said, do you write the paper for your province or write the paper for the journal? So I really admire your effort, really doing something that you can defend and doing something you are confident and you can help the province. I really admire you. And want to thank you again on behalf of Kumar and on behalf of the Fields Institute. Thank you for your interesting talk.
Thank you.
Thank you for the invitation. Thanks to everybody for coming. Yeah.
Bye.
Okay. Yeah. Bye. Have a nice day. Yeah.
You too. Bye.
Okay.